Bismillahirrahmanirrahim. Okay, we continue part 3 of chapter 4, Resonant Circuit. This topic will discuss about parallel RLC circuit, parallel RLC Resonant Circuit. So this figure shows simple parallel RLC circuit with current source and R, resistance, inductance and capacitance connected in parallel. From the figure, the input admittance, parallel we're talking about admittance, Y, which is equal to 1 over Z. Previous in series we talking about impedance. So in parallel we concerned about the admittance Y. Y is equivalent to inverse of Z, which is I over V. I over V is equal to admittance Y. So Y is equal to 1 over R plus J omega C plus 1 over J omega L. So as usual, this part can become negative. So if we use the negative sign, we have this J is on the top. So you can write in this form, Y equal to 1 over R, this part, and the imaginary part is omega C, which is this part, minus this part, 1 over omega L. This plus become negative when this J going upper side. Okay, so resonance occur when the imaginary part of this admittance or transfer function is equal to 0. Admittance is Y, transfer function is H omega. So when this imaginary part equal to 0, that is when the resonance happen. So we taking out this part, omega C minus 1 over omega L equal to 0. So solving that equation as shown in part 1, we will get the value of omega naught equal to 1 over RLC. This is known as resonant frequency omega naught with the unit of radian per second. And this is the voltage curve. Voltage over or voltage versus frequency. So this is equivalent to current curve in the series RLC circuit in previous slide, part 1. So from, as we have shown before, half power frequencies omega 1 and omega 2 can be calculated using this equation. So we can see that omega 1 equal to minus 1 over 2 RC plus this part, 1 over 2 RC square plus 1 over LC. And this one, this is minus, this is positive. Omega 2 is positive. 1 over RC plus 1 over 2 RC square plus 1 over LC. So what is omega 1 and omega 2? Hopefully still remember, omega 1 is the lower part of the frequency range, and omega 2 is the upper part, the higher part of the frequency range or frequency value. So from omega 1 to omega 2, that is called the bandwidth. Okay, parallel RLC circuit, the bandwidth is The frequency range from omega 2 to omega 1, or omega 1 to omega 2. So the bandwidth is omega 2 minus omega 1, equivalent to 1 over RC. The quality factor is this is the derivation of this equation can be shown has been shown in part 1. Q equal to omega naught over B. This is the definition of the quality factor. The frequency, the resonant frequency over bandwidth. So Q is also omega naught RC, equivalent to R over omega naught L. And for RLC circuit, for a circuit that having Q more than 10, it is considered high Q circuit. And when the circuit having a high quality value, we can, using the approximation equation, to calculate the omega 1 and omega 2. So same, we can use this equation as previous in series RLC circuit also. Omega 1 is omega naught minus half bandwidth, or B over 2, and omega 2, which is the higher part, is omega naught plus B over 2. So this is the summary of those slides. Parallel resonance RLC circuit. So we have this RLC in simple parallel circuit. So this is the voltage curve where the voltage plot against the frequency. We can see from here that the maximum voltage is at omega naught, which is the resonance frequency. So the admittance is I over V, and this equation 1 over R plus J omega C plus 1 over J omega L, where we can derive this, we can rewrite this in real and imaginary form, where Y equivalent to 1 over R plus J, the imaginary, omega C minus 1 over omega L. Resonance occurs when the imaginary part of Y is 0. So this imaginary becomes 0. That is when resonant frequency happens. So solving this omega C minus 1 omega L, 1 over omega L, equivalent to 0, solving this equation, we have omega naught equal to 1 over CERT LC, radian per second. This formula is valid if the circuit is simple series like this, simple series or simple parallel. And if the circuit have combination of series and parallel, then this equation is not valid. On the same line as we have done before in series circuit, it can be shown that B equal to omega 2 minus omega 1 equal to 1 over RC, and Q is omega naught over B, which is equivalent to omega naught RC equal to R omega naught over omega naught L. Summary. So the summary of some characteristic of resonant circuit. We have series and parallel. Basically, we have the concerned parameters are the frequency, resonant frequency, the Q, quality factor, the bandwidth B, half power frequencies, and omega naught if omega 1 and omega 2 when the circuit having high Q, meaning Q more than 10. So let's see. For series, we have resonant frequency 1 over RLC, similar to parallel circuit. So for both series and parallel, we have same equation for resonant frequency. Okay, next is quality factor. For quality factor, we have little bit different between series and parallel, where in series omega naught L over R or 1 over omega naught RC. For parallel, it is the reciprocal 1 over of this value, meaning for parallel we have R over omega naught L. In series we have omega naught L over R. So this is reciprocal, the 1 over Q. Whereas we have another one 1 over omega naught RC for series, and we have omega naught RC for parallel. So this is the reciprocal of this. Bandwidth is the same, which is omega naught over Q. Or this is or we can say that the bandwidth is same, which is omega 2 minus omega 1. Okay, half power frequency for low Q circuit, we can use this equation, but for high Q circuit, we can use this equation, the approximation equation, omega naught plus minus B2 for omega 1, and similar for parallel circuit, we can use this equation. So omega 1 is omega naught minus B2, omega 2 is omega naught plus B2. So similar. So the only difference is in terms of quality factor for series and parallel, which is, if we remember one, then we can remember another one, which is the reciprocal of that value. Okay, let's see one example before we end this slide. A parallel resonant circuit has a resistance of 2K and half power frequency of 86 kHz and 90 kHz. So what is this? This is the R value. This is omega 1 and this is omega 2. Determine A capacitance, B inductance, C resonant frequency, D bandwidth, E quality factor. So let's see how we solve this example, this question. So solution: bandwidth is omega 2 minus omega 1 equivalent to 2 pi f2 minus f1. So using this value 2 pi 90 minus 86, so we can get 8 pi k radian per second. 8 pi k radian per second. So omega naught is half of omega 1 plus omega 2. Omega naught is 176 pi multiplied by 10 to the power of 3, or 167 pi k radian per second. B, from this equation, B equal to 1 over RC, we can calculate the capacitance value, which is 1 over BR, 1 over B, this value B. R is given 2 kilo, sorry, R is given 2 kilo, so we can have the value of C, which is 19.89 nanofarad. B is the value of inductance. So from this equation, resonant frequency is 1 over RLC. We know the value of C, so we can calculate the value of L. So L, solving this equation for L, so 1 over omega naught square C equivalent to this value. So we get the inductance value of 164.45 microhenry. C omega naught is 100 76 pi. So multiply this, we can have 552.9 kilo radian per second. Bandwidth is 8 pi, B is 8 pi k radian, so 8 pi 25.13 kilo radian per second. E is the value of Q. Q is omega naught over B, so divide the value of omega naught with B, so we get 22. So the value of Q is, the quality factor is 22. So this circuit can be considered as high Q, and because the value is more than 10. So that's all. Thank you very much.